welcome to this problem walkthrough. Today, we'll be tackling problem number 1594, titled Maximum Non-Negative Product in a Matrix. In this video, we'll explore the problem statement, break it down step by step, and discuss potential approaches to solve it effectively. Let's dive right in. In this problem, we are tasked with finding the maximum non-negative product of any path within an mxn integer grid. Each cell in the grid contains an integer, which could be positive, negative, or zero. A path is defined as a sequence of cells that starts from the top left corner and ends at the bottom right corner of the grid. The movement is restricted to only two directions, down or right. The product of a path is calculated as the product of all the integers in the cells along that path. Our goal is to return the maximum non-negative product, with the result taken modulo 10 to the power of 9 plus 7. However, if the maximum product is negative, then we simply return -1. The grid has some constraints. Its size is small, with dimensions at most 15 by 15, and the values in the grid range from -100 to 100. This means we need to carefully handle cases where the product might involve negative numbers or zeros. To understand this better, let's look at a few examples. First, consider a grid where the input is a 3 by 3 matrix, 1, -2, 1, 1, -2, 1, 3, -4, 1. Here, the output is 8. Why? Because the path that maximizes the product is 1, 1, 3, -4, 1. If we multiply these values together, we get 1 times 1 times 3 times -4 times 1, which results in 8. This shows how we can navigate through the grid and calculate the product along a specific path while adhering to the movement restrictions of only going down or right. Now, let's consider another example where the input grid is 1, 3, 0, -4. In this case, the output is 0. The reasoning here is that the path 1, 3, 0, -4 produces a product of 0 because the presence of a 0 in the path causes the entire product to become 0. Since 0 is non-negative, it turns out to be the maximum non-negative product for this grid. This highlights the importance of considering how zeros in the grid can affect the overall product of a path. Finally, let's take one more example to illustrate this further. Suppose the input grid is 1, 4, 4, 0, -2, 0, 0, 1, 1, -1, 1, 1. Here, the output is 2. While the path 1, 4, 4 yields the highest non-negative product of 16, the presence of zeros in other paths affects the calculation. The result is adjusted to 2 based on the constraints of the problem. Speaking of constraints, remember that the grid size is limited to 15 by 15, and the values range from -100 to 100. This allows us to use techniques like dynamic programming or even exhaustive search due to the small size. However, we need to carefully handle edge cases, such as grids filled entirely with zeros, paths that include both positive and negative numbers, or grids where all values are the same. Even in a simple 1-by-1 grid, where there's only one possible path, the rules for returning the modulo result or -1 still apply. To solve this problem, we first considered the brute force approach. This method involves generating all possible paths from the top left corner of the grid to the bottom right corner. For each path, we calculate the product of all elements along the way and track the maximum non-negative product we encounter. While this approach guarantees correctness, it comes with a significant drawback. The number of paths grows exponentially with the size of the grid because at each step, we have two choices: move right or move down. This results in a time complexity of O(2)m plus n, which becomes computationally infeasible for larger grids. While conceptually simple, the brute force approach is impractical for grids beyond a very small size. To address this inefficiency, we need a more scalable strategy that avoids redundant computations and handles the problem more effectively. A more efficient solution lies in using dynamic programming. The core idea here is to avoid explicitly exploring all paths by leveraging overlapping subproblems. We define two dynamic programming tables, one to track the maximum product achievable at each cell and the other to track the minimum product. Tracking both is crucial because multiplying two negative values can yield a positive product, which may be the maximum for the grid. The recurrence relations describe how to update these tables. If we move down from the cell above, we calculate the maximum and minimum products by considering both the maximum and minimum values at the previous cell. Similarly, if we move right from the cell to the left, we apply the same logic. The base case starts with the value of the top left cell, and as we propagate these calculations through the grid, we eventually compute the maximum product for the bottom right cell. This approach ensures we avoid redundant computations and achieve a time complexity of O(m*(n), with space complexity also being O(m*(n), though this can be optimized further. Considering the trade-offs, we chose the dynamic programming approach for its efficiency and scalability. While the brute force method is simpler conceptually, its exponential complexity makes it unsuitable for even moderately sized grids. The DP approach, on the other hand, avoids recomputation by utilizing overlapping subproblems, making it significantly faster. One trade-off is the memory usage, as the DP tables require O(m*(n) space. However, this can be optimized to O(n) using rolling arrays. The linear time complexity relative to the grid size ensures that the DP solution can handle constraints of up to 10,000 cells, making it highly efficient. Additionally, tracking both the maximum and minimum products at each cell guarantees correctness, even for grids with negative numbers or zeros. This robustness makes the DP approach ideal for all edge cases, striking the right balance between performance and clarity of implementation. To solve this problem, we need to find the maximum non-negative product of any path from the top left corner to the bottom right corner of an MXN grid. The key constraint is that we can only move right or down at each step. The challenge arises because the grid can contain negative numbers, which means the product can flip signs along the way. This makes a brute force approach, which would explore all possible paths, computationally expensive and impractical for larger grids. Instead, we use dynamic programming to optimize the solution. The idea is to maintain two separate tables, one to track the maximum product we can achieve at each position and another to track the minimum product. This is necessary because encountering a negative number can turn the current minimum into a new maximum, and vice versa. We'll initialize these tables such that all positions are 0, except for the starting cell, where we set the initial value based on the grid itself. With this setup, we can efficiently compute the desired result while carefully handling the sign changes introduced by negative numbers. At the starting cell, 0, 0, both the max_dp and min_dp tables are initialized to the value of the grid at that position. This gives us a clear base case to work from. As we iterate through the grid, the transition function becomes the core of the algorithm. For each cell, I, j, the maximum product is calculated by considering the maximum and minimum products from its neighboring cells. Specifically, we look at the cell directly above, I1, j, and the cell to the left, I, j1. By multiplying these values with the current grid value, we determine the new maximum and minimum products for I, j. This ensures that even if we encounter a negative number, which could flip the sign of the product, we are still accounting for all possibilities. The same logic applies to updating the min_dp table, where we track the smallest possible product at each step. These computations allow us to efficiently propagate the maximum and minimum products across the grid without having to explore every possible path explicitly. For edge cases, such as when a cell is in the top row or the leftmost column, we need to handle the fact that it only has one neighboring cell. For example, a cell in the top row can only inherit values from the cell to its left, while a cell in the leftmost column can only inherit values from the cell above it. Once all the cells are processed, the result of the problem is found in max_dp, M1, N1, which represents the maximum product achievable at the bottom right corner of the grid. If this value is negative, it indicates that no valid non-negative product exists, so we return -1. The key insight here is that tracking both the maximum and minimum products is essential because of the possibility of sign flips caused by negative numbers. Additionally, special attention must be given to zeros in the grid, as any product involving 0 becomes 0. This approach ensures we handle all possible scenarios, including single-row or single-column grids, without running into out-of-bound errors. To implement this efficiently, we rely on two key data structures, the max_dp and min_dp tables, which are 2D arrays that store intermediate results for each cell. These tables allow us to access previously computed values in constant time, making the algorithm very efficient. The grid itself serves as a reference for the values at each step. When analyzing the complexity, the time complexity is O(m*(n), because we process each cell in the MXN grid and only depend on its immediate neighbors. The space complexity is also O, M**n, due to the storage requirements of the two DP tables. However, we can optimize the space complexity further by using just two rows, one for the current row and one for the previous row, reducing it to O, N, where N is the number of columns. This optimization is particularly useful for grids with a large number of rows. Overall, the algorithm is both time and space efficient, making it suitable for solving this problem even with larger grids. To illustrate the algorithm, consider this input grid: 1, -2, 1, 2, 3, -4, -1, 0, 2. Starting at 0, 0, we initialize max_dp 0, 0 and min_dp 0, 0 to 1, which is the value of the grid at that cell. At 0, 1, we calculate the products based on the left neighbor, resulting in both max_dp 0, 1 and min_dp 0, 1 being -2. We continue this process for each cell, updating the DP tables based on the values in the grid and the neighboring cells. Eventually, at the bottom right corner, 2, 2, we find that the maximum product is 12. This is the result of the path that maximizes the product while avoiding sign flips that would make it negative. Additionally, we can optimize the algorithm further by reducing space complexity to O, N, using two rows for the DP tables. To handle edge cases, we could implement early termination if intermediate results become irrelevant or exceed practical limits. This ensures that our solution is both efficient and robust. Here, we start by defining a class named solution and a method called maxProductPath that takes a 2D grid as input. The first step inside the method is to define the modulo value, mod, as 10 to the power of 9 plus 7, which will be used later to ensure our result fits within the constraints. Next, we capture the dimensions of the grid, with M being the number of rows and N being the number of columns. To solve the problem, we use dynamic programming and initialize two 2D arrays, min_dp and max_dp, both of size M by N. These arrays will store the minimum and maximum products achievable at each cell as we traverse the grid. We then handle the base case, which is the top left cell of the grid. Since this is where we start, both min_dp 0, 0 and max_dp 0, 0 are set to the value of grid 0, 0. After establishing the base case, we process the first row by iterating through its columns. Each cell's value is computed by multiplying the previous cell's maximum product with the current grid value, as there is only one possible path along the first row. Similarly, for the first column, we iterate through its rows, updating each cell's value by multiplying the previous row's maximum product with the current grid value, as the path here is restricted to moving downwards. Now, we focus on filling the rest of the grid, which involves handling both positive and negative values. For each cell, the calculation depends on whether the current grid value is positive or negative. If the value is negative, the maximum product at that cell is derived from the smaller of the two possible products either coming from the left or from above and then multiplying it by the current grid value. Conversely, the minimum product is derived from the larger of the two products and multiplied by the current grid value. On the other hand, if the grid value is positive, the maximum product is calculated using the larger previous product, while the minimum product uses the smaller one, with both being multiplied by the current grid value. Once we finish processing the entire grid, the maximum product at the bottom right corner is stored in max_dp -1 -1. If this result is non-negative, we return it modulo mod to ensure it meets the constraints. If the result is negative, we return -1, as a non-negative product cannot be formed. Here, we begin by importing the necessary utilities and defining the solution class. The method maxProductPath is designed to find the maximum non-negative product in the matrix. We start by defining a constant mod to handle large numbers and ensure our results fit within the required constraints. The dimensions of the grid, M and N, are determined based on the input matrix. Next, we create two dynamic programming arrays, minDP and maxDP, to track the minimum and maximum products at each cell. These arrays are critical because the product can become negative when multiplying by a negative number, so we need to track both the smallest and largest possible values at each step. The base case initializes the top left corner of both arrays with the value of the grid at that position. Following that, we fill the first row and first column of the arrays by propagating the product values along the edges of the grid, as these cells can only be reached from one direction. This setup lays the foundation for solving the rest of the matrix. Now, we proceed to calculate the values for the rest of the dynamic programming arrays. For each cell starting from position 1, 1, we evaluate whether the current grid value is negative or not. If it is negative, the logic reverses because the product of a negative number with the smallest product so far could yield the largest product, and vice versa. In this case, we compute max dp, I, j, by taking the smaller value between the upward and leftward cells in min dp, multiplying it by the current grid value. Similarly, we calculate min dp, I, j, by taking the larger value from the upward and leftward cells in max dp and multiplying it by the grid value. If the grid value is non-negative, the logic is straightforward. The maximum product comes from the larger value between the previous upward and leftward cells, and the minimum product comes from the smaller value. After completing the entire grid, the result is stored in the bottom right corner of max dp. If this result is non-negative, we return it modulo mod. Otherwise, we return -1 to signify that no non-negative product path exists. To solve this problem, we start by analyzing a small grid with positive, negative, and 0 values. The grid has 3 rows and 3 columns, so we initialize 2 matrices, min_dp and max_dp, to keep track of the minimum and maximum product values at each cell. The starting cell, which is the top left corner, 0, 0, is initialized with the value of the grid at that position, which is 1. Next, we fill the first row by calculating the product of the values sequentially. For example, at column 1, the product is 1 times -2, resulting in -2 for both minimum and maximum values. Similarly, at column 2, the product is -2 times 3, giving -6 as both the minimum and maximum. For the first column, the calculations are similar, but this time we move row by row. At row 1, the product is 1 times 4, resulting in 4 for both minimum and maximum values. Continuing with the first column, at row 2, the product is 4 times 7, resulting in 28 for both min_dp and max_dp. Now, we move on to filling the rest of the grid. At cell 1, 1, the value is -5, which is negative, so we swap the roles of minimum and maximum products. The maximum product at this cell is calculated as the smaller of min_dp, 0, 1, and min_dp, 1, 0, multiplied by -5, which gives 10. The minimum product is calculated as the larger of max_dp, 0, 1, and max_dp, 1, 0, multiplied by -5, which results in -20. This process continues for the rest of the cells, updating the min_dp and max_dp matrices depending on whether the grid value is positive or negative. Finally, at the bottom right corner, 2, 2, the maximum product is calculated to be 20160. Since the result must be returned modulo 10 to the power of 9 plus 7, the final output is 20,160. In this next example, the grid includes a 0, which adds an important consideration to our calculations. As before, we start with initialization, setting min_dp, 0, 0, and max_dp, 0, 0, to the value at the top left corner, which is 1. Then, we fill the first row and column. The first row is straightforward, values are multiplied sequentially. However, in the first column, we encounter a 0 at position 1, 0. This means both min_dp and max_dp at this cell become 0. Now, as we proceed to fill the rest of the grid, special care is taken to handle 0 correctly. For instance, at cell 1, 1, the value is -1, and since the maximum product of the top or left cells is 0, the maximum product at this cell also becomes 0. The minimum product, however, is calculated as -1. Continuing this process for all cells, we eventually calculate the maximum product at the bottom right corner, 2, 2, as 120, and this becomes the final output. Now, let's consider a grid where all the values are negative. In this case, the calculations leverage the fact that multiplying two negative numbers results in a positive number. We initialize the top left corner of the matrices with the grid value, which is -1. Moving across the first row, we calculate the products sequentially, resulting in values of -1 and 2 for min_dp and max_dp, respectively. Similarly, for the first column, the products are calculated sequentially, giving values of -1 and 3. As we proceed to the rest of the grid, we carefully handle the sign of the values. At cell 1, 1, the value is -4, which is negative. To calculate the maximum product, we take the smaller of the minimum products from the top and left cells, multiply it by -4, and get 12. This is because multiplying by a negative number flips the sign, turning the smallest negative value into the largest positive one. At cell 1, 1, the minimum product is calculated as the larger of the maximum products from the top and left cells, multiplied by -4, resulting in -8. With the rest of the grid filled using this approach, we find that the maximum product at the bottom right corner is 12. Since there are no additional modulo constraints in this example, the final output is simply 12. This demonstrates how the algorithm handles grids with all negative values effectively, leveraging the sign flip caused by multiplication with negative numbers to ensure the correct maximum product is computed. The time complexity of this solution is O(m*n), where m represents the number of rows and n represents the number of columns in the grid. To understand this, let's break it into smaller steps. First, we initialize two 2D arrays, min_dp and max_dp, each of size mxn. This initialization step alone takes O(m*n) time. Next, we handle the first row and the first column. For the first row, we iterate through all the columns, which takes O(n) time, and similarly, iterating through all rows for the first column takes O(m) time. Finally, we process the rest of the grid. For each cell, we calculate the minimum and maximum product based on values from the top and left neighbors. This operation is repeated for every cell except those in the first row and column, which amounts to m1*n1 cells. Since this step also requires O(1) operations per cell, it totals to O(m*n). When we combine all these steps, the dominant factor is the grid traversal, resulting in an overall time complexity of O(m*n). The space complexity of this solution is O(m*n) due to the use of two 2D arrays, min_dp and max_dp, each of size mxn. These arrays are necessary to store the minimum and maximum product values for each cell in the grid. Beyond the DP arrays, the input grid itself does not contribute to additional space usage because it remains unchanged throughout the algorithm, so it counts only as part of the input size. Additionally, the algorithm uses a constant amount of auxiliary space for variables such as mod, m, n, and the loop counters, which together require O(1) space. When we sum up the space usage, the dominant factor is the size of the DP arrays, resulting in an overall space complexity of O(m*n). A naive brute force approach would involve generating all possible paths from the top left to the bottom right corner of the grid and calculating the product for each path. This approach is highly inefficient because the number of paths in a grid grows exponentially, with O(2)m+n paths in a grid of size mxn. Evaluating each path would take O(k) time, where k is the number of paths, making the brute force method impractical for larger grids. In contrast, the optimized dynamic programming approach avoids this exponential growth by storing intermediate results in the min_dp and max_dp arrays. This reduces the time complexity to O(m*n), which is much more efficient and scalable. The space complexity of O(m*n) is also reasonable since we only store the minimum and maximum product values for each cell, rather than tracking every possible path. In the best-case scenario, where the grid has only one cell, such as in a 1x1 grid, the algorithm performs only the initialization step and directly returns the value of that single cell. This results in a time complexity of O(1). For average and worst cases, the algorithm must traverse every cell in the grid. This means that the time complexity is consistently O(m*n), regardless of the grid's composition. The worst case occurs when the grid contains a mix of positive and negative values, which forces the algorithm to fully utilize both the min_dp and max_dp arrays to track the possible products. To formally analyze this, we can break it down mathematically. Initializing the DP arrays takes O(m*n). Filling the first row and column adds O(m+n). The rest of the grid traversal involves iterating over all m*n cells, with constant time operations at each cell. This confirms that the total time complexity is O(m*n). Similarly, the two mxndp arrays dominate the space requirements, leading to a space complexity of O(m*n). When solving this problem, there are several common pitfalls to watch out for. First, misunderstanding the problem constraints is a frequent issue. It's essential to carefully analyze details such as the grid dimensions, the range of elements, and whether the grid includes negative numbers. Overlooking these constraints can lead to incorrect assumptions and ultimately to invalid solutions. Another mistake is neglecting edge cases during testing. Scenarios like grids with just a single row or column, or those where all elements are negative, are often missed. Writing test cases specifically for these situations helps ensure your solution is robust. Additionally, relying on inefficient brute force methods can be problematic, especially for larger grids where optimization is crucial. Techniques like dynamic programming or memoization are often necessary to meet time complexity requirements. Finally, an incorrect approach to calculating the path product can also trip up candidates. This is particularly true when dealing with grids that include both positive and negative numbers, where managing the signs properly is key to avoiding errors. Now, let's delve into more nuanced challenges and strategies. Overcomplicating the transition logic is another common hurdle, especially when implementing a dynamic programming solution. It's important to define the recurrence relation clearly and keep the state transitions as straightforward as possible to avoid introducing bugs and making your code harder to debug. Interviewers also often explore problem variations, so be prepared for requests like finding the minimum product path, navigating grids with obstacles, or even optimizing memory usage. Flexibility in adapting your solution to these variations is highly valued. When explaining your approach, start with the brute force method to establish a baseline, then identify bottlenecks and demonstrate how you optimize using dynamic programming or other techniques. Make sure to articulate the trade-offs between time and space complexity. Lastly, thorough testing is non-negotiable. Always validate your solution with edge cases, such as a grid with a single cell, a grid filled with zeros, or one with alternating positive and negative numbers. This demonstrates your attention to detail and ensures your solution is comprehensive. To deepen your understanding of this problem, it's helpful to explore related problems. For instance, LeetCode 64, Minimum Path Sum, focuses on a similar grid traversal concept but seeks the smallest path sum instead of the maximum product. LeetCode 174, Dungeon Game, involves maintaining both minimum and maximum values along the path due to health constraints. LeetCode 221, Maximal Square, and LeetCode 980, Unique Paths 3, also share overlapping principles, offering more opportunities to practice grid-based challenges. In terms of alternative approaches, dynamic programming remains the most efficient for most scenarios, though its space complexity can be high for large grids. To address this, you can use space reduction techniques like rolling arrays. Depth-first search with memoization is another option, particularly for smaller grids, but it can lead to stack overflow or excessive memory usage in deeper recursions. Greedy approaches may suffice for specific cases, such as non-negative grids, but they often fail in general scenarios involving negative numbers. Lastly, graph-based shortest path algorithms can be useful when additional constraints like weights or obstacles are present, though they're typically overkill for simpler grid traversal problems. By exploring these methods, you'll be well equipped to handle variations and optimize your solutions effectively. Great job on completing this problem. To sum up, we explored the brute force approach and discussed optimizations to improve efficiency. Remember to practice similar problems to solidify your understanding of dynamic programming and matrix traversal techniques. Thank you for watching, and don't forget to like and subscribe for more tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!